and different scenarios. So let's see, we have this nice set of equations, and the next thing we're going to do is we're going to put this equations on the top right, and we're going to implement it. So in order for us to be able to run this, I need some information beforehand. So the first thing I'm going to establish is the initial number of individuals at day 0. So that's the very first bullet that you see there. So this community has 20 individuals, 19 of them are susceptible, 1 of them is infected, and none of them have recovered from anything. The next item is we have to establish values for those parameters beta and gamma. Normally that information is obtained from real world data. Sometimes that's not possible, and other techniques are done just to get some sort of estimates for those values. For this example, I just chose those 2 numbers. So beta is equal to 0.04 and gamma is equal to 0.1. And finally, another assumption that we're going to make is that in this community, just like in the very first slide, people are not coming in and out of the community. So we're just gonna put him on an island, for instance, and then let the disease run its course through the entire community in this island and see what happens. So to compute the very first forecast or the very first prediction at day 1, so we set the value of t is equal to 0, and then I'm gonna use the values in the first bullet and plug them into the equation that you see there. So taking all those values of 19 and 1, I put them in their appropriate places. Then of course I plug in the value for beta, and using my calculator, I get an approximation for that to be 18.24. I do the same thing for the second equation. I take those same values of 19 and 1 and plug them in, and using my just a standard calculator, simplify all that, and we get 1.66. I'm not going to do this for the last equation R. It's not necessary. We could do that, but for the purposes of this presentation, I'm only going to focus on those 2. And in fact, only focusing on those 2 would be sufficient for solving this equation. And one of the reasons is what Dr. Barnaby pointed out earlier, because there is no interaction between R's and S's explicitly. So you'll notice that the first equations don't have an R in them. So we can decouple that from the other 2. And then if we wanted to continue, then we set t is equal to 1, and we perform the same exact process, except this time I'm going to use 18.24 and 1.66, which were obtained previously, plug them all in, and I get 17.03, and then the I of 2 would be found in the same way. And we can do this forever. We can go as far out as we want. So I take all of these numerical values and we organize them into a table. So I only will consider the susceptible and infected class, and that table is on the left-hand side. On the right-hand side, I have this little animation that was created here as well. The blue dots represent the individuals that are not sick, the red ones, the individuals that are sick, and then the green ones that are recovered. So as we run through these different values of t is equal to 0, 1, and so forth, you will see that the blue dots and the red dots begin to change. So this is telling us how this disease is spreading along the community. You begin to see some recovered individuals as well. So this is over a course of 18 units of time. So we never defined what the units of time were. They could be seconds, they could be minutes, they could be hours, they could be weeks. And finally, we go all the way up to the 12th one. And that's the very last one. And so this disease, we run its course for over the course of 12 units of time. But what I want to look at in particular are the time values between 6 and 11. And I want to also focus on those 2 highlighted columns, the one for the infected class. And if you look at the value for t is equal to 6, you will notice that it's 11.53. And as I'm going down, I get to 13.5. And then those values begin to decrease again. So it appears that we have some sort of peak just from looking at these numerical values. So I'm going to take those 2 columns and I'm going to organize them like this. And I'm going to draw a bar graph for these data points. And then I look at the region right below with the brace, and you will see that that's where the peak occurred, corresponding to the highlighted numbers there. And I then fit a curve, and I clean it up. I remove all the curve and all those points. And here we have that famous curve that we have been seeing in the media all this time.
All right, so that was, thanks Dr. Melara for that introduction on how these SIR models work. So now I'm going to talk about extending this to make it more specific to looking at the coronavirus, and we're going to move to a continuous model using ordinary differential equations, which if you don't know what those are, we're gonna talk about those first, and then we will look at the model. But we'll start again with this flow chart kind of idea. So we know we should still have a susceptible, infected, and a recovered population. The susceptible will become infected at a rate beta, and then the infecteds become recovered at that same rate, at a rate gamma, different numbers. But with the coronavirus, we know there's other things that are happening. For example, right, we do know that unfortunately people have been dying from this disease. So we have to have people leaving the infected population and dying, and I have it at some rate delta. We also know that we have been forced to quarantine ourselves, right? So we have a quarantined population. The susceptible are going to have been moved into quarantine at a rate alpha sub 1, and then the infected also should be quarantined, and I have them as two separate quarantine populations for the sake of that the people who are infected that have become quarantined after becoming sick, there's two options with those quarantined people. Either they could die still from the disease, or they can recover at the same rate. So I have the recovery rates and the death rates the same, but this quarantine population over here, the susceptible population, in theory, should not, right there, they shouldn't be coming in infected, so that population, right, should be staying there safely away from the disease. And we're going to assume that there's no one else entering the population, so we're going to not have any new births, and we're going to ignore death due to anything other than the coronavirus, just to keep, like Dr. Melara said before, just to keep it as simple as possible, because we've already made it a lot more complicated. Oh dear. Okay, can we all see that now? Sorry. Okay. So, like I said, we are going to make this into an ODE model, ordinary differential equation model. So the way you want to think about an ordinary differential equation, if you don't know what it is basically it's an equation that looks how some population varies with time. So all these fractions on the left-hand side of the equal sign, right, say susceptible over time, infected over time. So that's just going to be how these populations vary with time. The right-hand sides of all of these equations are going to be basically almost the exact same things as in the previous model that we looked at, right? The how these populations, what's causing these changes with time. For example, the susceptible population, when it comes in contact with someone who's infected, should leave the susceptible population. Also, we have that the susceptibles need to be quarantined. So this next term is the susceptibles leaving the susceptible population and moving to this first quarantined population. Similarly, we have that there's going to be more infected people when a susceptible comes in contact with the infected. They will move from the susceptible population to the infected population. And then either the infected can become recovered, the infected can move to quarantine, or the infected can die. And then we have our recovered population. So the recovered either come from an infected, directly from the infected population recovering, or those infected that move to quarantine can also recover. And then we have our two quarantine populations. So I have the quarantine from the susceptible, so susceptibles moving to quarantine, and then I have the infected moving to their quarantine. And these infected people in quarantine can either recover or they can die. So we can take these word equations and we can turn them into a system of ordinary differential equations. And I have the little flow chart, the SIR schematic up in the corner. And you can see, right, we have the same types of multiplications, additions and subtractions that we had from before, except now we've just added some more complexity to these equations. So they look really similar to the first model, except we have this added quarantining effect in the susceptible and infected populations, as well as this included death terms. And so what we looked at next was taking these equations that describe what's happening in the population with the coronavirus, and we have these 5 parameters: beta, alpha 1, alpha 2, gamma, and delta. And we wanted to try to estimate what those parameters were using some real world data. And like Dr. Melara said, there's a lot of data out there. And the best data I could find, where I actually was able to find data for the infected population as well as the dead population with each day, was national data. So I fit this to national data starting on February 15th. So day 0 for both of these is February 15th, and it runs out until April 5th is my last data point. And so I was able to fit, so what you see in the red dots is the data that I was able to get. The curves you see, the lines, are my fits to this data. So I was able to use MATLAB using a built-in package called LSQ Curve Fit, and it will solve for me those parameter values. And we can see we get a pretty good fit to the data, right? This line fits this data pretty well. And down here we see the res norm. And so that number is pretty small. And basically what the res norm does is it looks at the difference between the data point and the fit. So it's calculating an error between the data point and the fit. And so the smaller your res norm, in theory, the better your fit is. And so you can see we were able to get a decent fit to data. So like I said, this went until April 5th, but it is now April 16th, so more days have passed, and so more data was collected. And so what I decided to do next was, in the blue were the data points from April 7th until April 13th. So it kept the same fit that I had done on April 5th, and I just plotted the data points for April 7th through the 13th. And so you can see that here on the left, the infected, it's pretty close that my fit is fitting to what's happening in the real world, but you can see it's slightly overestimating on the infected side. It's still fitting the number of deaths pretty well, but we can see that it is a slightly overestimating it. Now, what we're really interested in, right, is the curve, right? What is this infected population going to look like as we go out in time? And the nice thing about running these simulations is I can just run my simulation for the rest of time, really, if I wanted to. But for a foreseeable future, I can run it out and see what happens. And these are the curves that we're all being shown and it's being produced.